Thanks for a nice introduction. It's great to be here in our Open System Day today to talk about this work on designing quantum Markov Chain Monte Carlo algorithms. This joint work with very nice people here, and Andras was just giving a previous talk. You can think of this talk as like a part 2, or you can think of it as like a complementary view of the previous talk. Like the previous one is like, oh, open system, how do we simulate it? It's more like a nature inspired, or like, we just want to simulate nature. But here, we're really trying to take a very computer science approach. A lot of things are going to be the same mathematically, but somehow the picture is quite different. So today, the theme is just, let's design a Markov Chain Monte Carlo algorithm, but now you have a quantum computer. And now you can store a quantum state. And what does that mean? And we're going to present this algorithm. It will end up being almost the same as the open system simulation, but with a little bit tiny differences, but lots of conceptual differences. And maybe let me investigate the background. So are people here more from physics or computer science, applied math? OK, that's perfect. And I know you guys love Markov Chain Monte Carlo, so yeah. I'm not sure.
Sorry, are you talking about the standard quantum Monte Carlo or something else?
Something else. You need a quantum computer. Yeah. Yeah. So the goal for today is to prepare a quantum Gibbs state. So you assume you have a quantum computer. You want to prepare a quantum Gibbs state in your quantum memory using a quantum algorithm. Now you can think of this as very similar to a classical setting. You're given a classical Ising model. You have a classical computer, and you want to prepare the Gibbs distribution on your classical memory. And you want to sample from that distribution. So this is a quantum analog of that. So quantum Gibbs sampling, this is another way to put this. For those of you who are not from physics, this rho beta is called Gibbs state. It's parameterized by a parameter beta. It's the inverse of the temperature. So this guy is diagonal in the Hamiltonian basis. So these guys are the eigenstates. And these eigenstates are weighted by some exponential. So it's called a Boltzmann factor. So what's happened here is that they want to suppress the high energy state and favors the lower energy ones. So this physicist told you this is the nice object to think about. And in particular, if beta is super large, this would be the ground state. Right? If beta is 0, then all these factors are the same. So this is just a uniform mixture. So it's the infinite temperature state. Yeah, so you want to prepare this guy. And of course, this problem depends a lot on the Hamiltonian. Right? If the Hamiltonian is pretty complicated, it might be really difficult. For easier Hamiltonian, this is pretty simple. Right, so at this point, if you're a computer scientist or mathematicians, you can already start thinking about this problem, like how would you do this and design a quantum algorithm. But since there's some industry activities around, I want to give like a practical motivation. You probably have heard this motivation a gazillion times. But suppose you can run Gibbs sampling. You can prepare quantum Gibbs state. One thing that you might want to do is to use it to simulate quantum system, right? To simulate low temperature physics. So you can put your favorite molecule or condensed matter system there and put your favorite property of low energy physics. And you can imagine if you want to design a quantum algorithm, there are sorts of things that you would do like this. You want to start with a good state, like a ground state. You want to do some time evolution and do some measurements. And you can imagine yourself calculating some correlation function, some observables at low temperature, right? Just as how you do it in your lab, right? You would do all sorts of combination of these tools. However, as of today, it still seems pretty mysterious how you actually prepare the initial state. Right, if you look at some of these papers, it's already kind of outdated, but there's some discussion there that some of the industry people actually try to calculate how this would look like. Suppose you want to get some understanding of some kind of chemical property, what would you do? And in the end, this step of state preparation still remain very mysterious. We don't quite know how expensive it would be. And usually people use this ansatz like adiabatic evolution and then applying phase estimation. This has been fairly well understood to the extent that it can be analyzed. But today we're going to approach this by a quite different algorithm. Okay. Our approach we're going to take as already alluded for the whole day, is that we're going to think of this from open system. So if you ask, how do these states actually appear in nature? Well, it comes from a refrigerator, right? So it's very natural just to take a step back and just think, well, why don't we just try to imitate that, right? Whatever nature is doing, let's try to learn that, and maybe we can do it even better, right? So indeed, if you ask physicists, they would tell you that, well, how do you prepare a Gibbs state? You just put it in a refrigerator. But somehow it has been really difficult to make very rigorous statements on that. Like, for example, how would you write down this process? How would you write down Lindbladian that captures cooling? So we already have some discussion from the last talk. But somehow it's still not like a consensus of like what you should look at, and there's been a lacking of quantum algorithms that describe this process. Yeah. So therefore, our goal for today is to capture that very precisely and use that as an inspiration to cook up an algorithm that does this. So basically, it's a cooling algorithm. And it turns out you can think of this as a quantum MCMC algorithm. Okay.
So for physicists, when they actually do the cooling process, are they happy with the state they got, or they just believe it's the right state?
Well, I mean, if you're in a lab, you just measure it and then start. Like you wouldn't. It's really hard to say more, right? You can do tomography, but
right. But do people just believe the way?
Yeah, they would just say, oh, let's suppose that my system is in a ground state and do some calculation, and then see that, oh, maybe there's some match, but there might be some noise, whatever. Like, but it's really hard to get more precise because it's hard to do like a full tomography of your state in your analog device. Yeah.
One question, I think, a follow-up actually for the next talk, is some of these energy levels are very close, right? Then is it not even impossible to really separate them and create that?
Exactly, and that's why this has been so mysterious. That's why this is so mysterious. So you have that infinite time, like almost a physical one. So you can look at that, but it's not what happens in nature, because nature cannot distinguish exponentially close levels.
So in some sense, you don't really have a chance. You can only do it approximately.
Yeah, so you really only do it approximately, and that brings a lot of trouble. Yeah, and that's why it's been so mysterious. Like it seems like a problem that people should have been solving, right? Okay. So for today, this is the main object we talk about. This is the title. Is that we're going to present a quantum MCMC algorithm, and you'll see what it means. But what it is something that's very close to what happens in nature. We take inspiration from it. So from open system, there are lots of nice physics. And then in some sense, our algorithm is a very formal, almost a definition of some of these processes. But it's not exactly the same because we're algorithm designer. We can tweak, we can change the algorithm. But in spirit, it's very, very similar to what happens in nature. It's a Lindbladian. However, today I'm going to focus more on the computer science perspective, is to view this from an angle of classical Markov chain. So indeed, in the classical world, people have been running Gibbs sampling algorithm for 70 years, I believe. Like metropolis sampling was invented 70 years ago. And that was what people was doing then. People were just trying to simulate properties of Ising model, precisely the thermal properties. People can see phase transition, all sorts of observables for lots of these Ising models. But then this Markov, these Monte Carlo methods has just ever since take off, and it's been widely applied to lots of other places. And nowadays, it's very hard to avoid Monte Carlo. In many other cases, not physical, but you will use them in some, say, optimization problem, even machine learning. So I would like to say that the thing we're going to present today is a quantized version of that. So you want to prepare the quantum Gibbs state using a quantum Markov chain, which is Lindbladian. So to make this analogy, I'll just start with some very quick background on classical Monte Carlo. So how many of you have taken a course on Markov chains? OK, so this should be a very quick review. So I just want to highlight some of the key ideas so then to see how they transfer to the quantum case. Okay. So very briefly, Markov Chain Monte Carlo is to design a Markov chain and then that you can implement on your computer. And then once you iterate the Markov chain for long enough time, you get the stationary distribution. Right? And then there are several things that you want. You want this Markov chain to be visually implementable. You want the Gibbs state to be your stationary state. Right? That's the thing you want. And then you'll be really happy if it converges quickly. Right? And then it's not always the case. Everything converges. Sometimes you get stuck somewhere. Sometimes you have to do some carefully chosen update, like this cluster update, so then you can actually mix this to the whole landscape. So this doesn't always work, but when it works, it's great. Right? And you can write down the general complexity if you want to prepare a good Gibbs sample. It's really just how long you're running the algorithm. Right? It's very well known that the mixing time kind of dictates the complexity of this algorithm. Yeah, and then over the past decades, people have been developing so many tools to analyze mixing times of various kind of Markov chains. Right, so this is almost like a standard textbook material. Okay. All right, so this is some intuitive examples. So this is one example of a Markov chain that's have 4 states, and then these weights are designed perfectly so that the stationary distribution is the Gibbs state. So here the Gibbs state is going to be exponential folding function, right? Because energy is changing this direction. Indeed, you have more weights going to that direction and less weights going this direction. So in this simple example, it seems Markov Chain Monte Carlo is pretty simple. But in realistic setting, it's actually not quite obvious how you choose these weights. Right? So there's a very nice recipe I want to show in this example. It's called detailed balance. In the last talk, this idea already came up, but now let me just tell you what it is. So detailed balance is a very commonly seen recipe in Markov chain designs so that it gives you the Gibbs state as the stationary state. So what it amounts to is to demand that the flow between any two pairs of configurations need to cancel out each other at stationarity. So mathematically, this is Boltzmann weight, and you multiply them by the weight, by the rate that they transfer to each other, and these two has to cancel out. And you can convince yourself that if this equality holds, then the Gibbs state will indeed be stationary, because every pair of flow cancel each other, so nothing changes. In terms of matrices, it looks like this, right? You write down your matrix, transition matrix M, and these are the configurations with sorted by the energies. And then detailed balance is the symmetry upon reflecting on the diagonal, right? So these two pairs have to be related to each other by the Boltzmann factor. Yeah, in this simple example, this is tridiagonal, so it's fairly intuitive. But then you could have more and more entries in weird places. And in principle, it might get really complicated. Yeah, but you want this symmetry. Right? So now, now we know that detailed balance is good. You can ask, how do we actually implement this very delicate-looking symmetry? Right? It's like there are so many equations that have to satisfy. So each pair of these points have to obey this. So there are lots of equality. So how would you actually do that? So there's another very nice algorithmic idea called rejection sampling that handled this almost magically. Right? So in principle, if you have very complicated Hamiltonian you want to understand, a priori you don't know how to write down this matrix. Right? This matrix has lots of elements. If you just write it down, it will just take exponential space. So how do you actually do that? So the idea here is called rejection sampling, which is what enables metropolis sampling, is that you can actually implement this Markov chain on the go. Now you only need to do rejection sampling whenever you see a transition that increases the energy. When you see that, you say that with some probability, I'm going to reject with a carefully chosen probability. Therefore, part of the energy increasing transition being canceled becomes weaker. And then if you choose this probability very carefully, then it corresponds to a detailed balance condition. So again, you're not writing down the full matrix. It's just that in your algorithm, whenever you see something, whenever you see an energy increasing transition, you do the according jumps. So this allows you to get detailed balance without storing the full matrix. So this is kind of really, really magical. Okay. So let me just end this quick review by showing the Metropolis Hastings algorithm. So this algorithm has been run for a very, very long time. People still use it. And as a user, all you need to do is to choose a Hamiltonian, for example, like Ising model. You can choose whatever parameters you like. And you choose an inverse temperature. And then you choose a set of jumps. Yeah, so these set of jumps, people have mentioned in last talk. In this case, these A are just local, single poly spin flips. You just flip it from up to down or down to up. Yeah, so once you specify the Hamiltonian and a set of jumps, you can run an algorithm. And this is an animation. So looks like this. Yeah, so what's happened? Okay, let's just play it again. Whew. Yeah, so let's just see this again. Yeah, so what happens is that when you run this algorithm, the energy starts decreasing, and at some point it stabilizes.
Can I ask about this rejection again? Because the only thing we can measure is if the global energy increases or decreases, right? We can't say anything about. So this still works, even though I can just have information about the global energy.
But yeah, classically, you just look at the energy. The energy is the whole thing. You just calculate that. You have configuration A. You flip a spin, and it becomes another configuration. You know the energy of both. You take the difference. Classically, this is direct. You just know what the energies are. Okay. All right, so that's the review of classical Monte Carlo. Hope you didn't fall asleep. So I'll just give you a laundry list of what you want. There's some classical configuration. There's the Gibbs distribution. There's some Ising model Hamiltonian, and there's some set of jumps. And then there's the famous algorithm, Metropolis Hastings, and then you get a fixed point by detailed balance. Okay. So now, for today, what we want to do is to fully quantize this idea. So you want to change from classical strings to quantum states. So there could be entanglement. So it will be difficult to store in your classical memory. Now you care about the Gibbs distribution, which is now it's an incoherent mixture, but it's mixed in the energy basis, which in principle could be very entangled. In principle, probably very difficult to write down in a classical computer. And a Hamiltonian could be non-commuting. Right? So it might be hard to do a classical simulation, but you can do quantum simulation. And then the set of jumps you can use, naturally you could think about polys, because like classical case, this would correspond to x, right? But in quantum case, you can have x, y, z, you can have like x, x, y, y, you can have liberal choice of jumps. But we should think of them as polys. That's convenient. And then the goal for today is to come up with the right generalization of this idea in a quantum case. So that's why I call it the quantum MCMC algorithm. We're really trying to make an analogy, line by line. Oh yeah, so in the classical, if you take out like a Markov Chain textbook, they will tell you like how you prove mixing in some cases. But mixing in general is very hard to prove. Like otherwise you would solve all the problems. Like you could put like an NP-hard problem to it, and probably wouldn't solve it. You probably get stuck somewhere. It means that it probably mix very slowly. Does that answer the question? I think still today people are working on proving mixing of particular classical Monte Carlo algorithms. It may not be so easy, like it would be case dependent. Okay. Yeah, so that comes to the main part of today, is that we want to design a quantum MCMC algorithm. So one thing you might be tempted to do is to say, well, why don't I just go to energy basis? Right, because the classical Gibbs state is just on the bit strings, and the quantum Gibbs state is on the energy states. So why don't I just write down like a 1D walk, and just put our eigenstate projectors here? Okay. So this seems fairly intuitive, right? And if you're able to just do a random walk on the eigenstates, then you can imagine that it reduces to another classical random walk. Right?
So this superscript on A is what?
Oh, this one?
Yeah.
This with a choice of jumps.
So the summing of all the possible jumps.
Oh yeah. Sorry, yeah. There should be sum over A. Yeah. Right. Yeah. So for different jumps, these transition rates could be different. No? Make sense? So this is indeed how people first approach this problem. However, there's one. The more you think about it, you realize it's not so trivial. The first challenge you encounter is that you have to do rejection sampling on an energy basis. And second, you also need to measure the energy very precisely, because energy eigenstates are very complicated objects, right? You don't really access them. You only access some kind of approximate versions of it. Right? So you can ask yourself, how would you actually implement this object? If you want to do a random walk on an energy eigenstate, how would you do it? Right? Suppose you start with the state here, and then you apply some operator, and then you measure it. And then it collapses here. How would you go back?
Measure with other bases?
Sorry?
Maybe measure with other bases.
Measure. Right, I didn't hear.
Sorry, I mean measure with another maybe set of bases, and you can go somewhere else.
Oh, but then you don't know the energy, right? How you want to both know energy, and then when energy increases, you reject. I didn't hear.
Do this process many times, you can average.
You might run into a problem with post-selection. Because when you fail, you want to say, no, I want to go back. Like when the energy increases, you want to go back to the previous states.
You have the rule, right? I mean, you know how if you invert I and j, there's this ratio condition, and usually you will just not be satisfied 99% of the time, right? The ratio between the left eigenvalue and the right eigenvalue, that will be violated most of the time.
Yeah, so you have to do something.
A alpha just will not work, period. Right?
Yeah, so that's why you need to do rejection. Like if you don't do anything, it will thermalize the maximum mixed state. You need to put some bias on the energy basis. Yeah. And the question is, how do you do that? Because if you measure it, it could collapse, but you still need to know the energy. So this is the main challenge.
So can you do this through the quantum random walk or quantum walk on a directed weighted graph? Then you have this bias, right? Imposed on all superposition of states.
Yeah, so if you want to do that, the question is, how would you end up with that access model? How do you implement that random walk? Because you're given some Hamiltonian.
Yes.
And you want to convert.
Yeah, so it's a continuous quantum walk with the e to the power of IAT, and that A is biased. It's directed and weighted.
Yeah, but you want to bias it exactly correspond to the energy. So you somehow need to know the energy. Right? If you start with this A, it doesn't know anything about the energy. So you really have to do some algorithm that tweak these transitions, and that's the question.
Yeah. Got it.
Why can't you get energy? You can just do phase estimation. Okay.
Well, if you do phase estimation, and then you just see, oh, energy is 10, then you're here. How would you go back?
Some kind of rewinding, because I think you have
Yeah, exactly. So you actually have to do that. But intuitively, this is pretty difficult. If you just measure it, then you can't go back. Yeah. So this is the main problem. So let me just repeat. The challenges in implementing such a random walk on an energy basis is that you want to measure things, but you also don't want to collapse it. Right? If you collapse, you really lose the previous state. But classically, it's fine because you can just remember the previous state. You can have like gazillion copies of it. But quantumly, you cannot clone it. Right? So there's a tension between no cloning and then doing rejection sampling. And as Yudong says, there's a trick called rewinding. It's a pretty complicated object that allows you to go back without actually measuring what's here. So that's possible, but it's quite complicated, and it makes the algorithm extremely hard to write down. But you can kind of do that. Okay. And the other one is more of an analytic question, because classically the energies could be, obtained at very high precision, right? But quantumly, it always have to involve some kind of measurements. Whenever you measure things are uncertain. So then you don't get exact detailed balance. It seems very likely you'll get some approximate version of it. And this is indeed what happens in the Davis generator business in the last talk. This parameter t roughly tells you how precise these bumps are. And because of this error, you don't get exactly a Gibbs state, but approximate Gibbs state. Okay. Yeah, so these are the challenges, but no, we claim to solve these challenges by presenting today's algorithm. There's no surprise, the algorithm takes the Lindbladian form. So you have seen these guys. So what we're going to do is just to implement this Lindbladian evolution, and that's our main object. We claim that this Lindbladian L has the following nice property. This is what we design in order to get these nice property. First, this generator can be implemented efficiently. It's built upon the algorithm Andras just described. And second, we design the Lindbladian very carefully such that it has detailed balance, the quantum version of detailed balance, such that the Gibbs state is the stationary state. With this too, it sounds like a Markov Chain Monte Carlo algorithm. But now everything is quantum. Therefore, you can write down the complexity per quantum Gibbs sample. It's going to be the cost per time, just to implement this exponential LT, multiplied by the quantum mixing time. Yeah, so now the complexity of Gibbs sample reduces to the mixing time.
In order for it to converge rapidly, do you require some condition on the original Hamiltonian?
Yeah, this would depend a lot on the Hamiltonian. Yeah. If you have some strongly interacting Hamiltonian, maybe the mixing time is long. If you have some spin glass, it probably mixes very slowly. If you have some simple Hamiltonian, it probably mixes very quickly. And sometimes, it might be that case that if you choose a jump correctly, it suddenly mixes very quickly. It's like in a classical case, you have cluster updates and suddenly everything works. But you might get stuck in other cases.
So in the quantum implementation of Markov chains, which is different from this, but I think there might be a similar issue with the preparation of the initial state. Do you need a big overlap between your initial density operator and the Gibbs?
Yeah, but here, if it's a Markov chain, it converges to the fixed point. Right? The mixing time is the time where any state converges to the same point. So in principle, you don't actually need, you can start with the maximum mixed state. Because it's dissipative, it can track everything to the same point. So then somehow this, in some sense, avoid the initial state problem.
So this is can be considered as a non-Hermitian quantum work, right? I mean, basically it's dissipative.
Yes.
Work.
Yes.
Yeah. and then that L is kind of non-symmetric and non-Hermitian. Is that that picture is still right?
Yeah, it's not norm preserving.
Yeah,
It contracts things.
that's right.
Yeah.
Yes. Yeah.
It's not unitary.
Yeah.
But there might be still some coherence. But it's like semi-classical. Some part is incoherent, some part is coherent. Oh. Right. So very quick review. We have seen this. Just want to display it. So the most general Lindbladian looks like this. There's a coherent part. There's a dissipative part, where this dissipative part has this weird-looking structure. And our goal is just to design these L. Right? And once you design them, you also want them to be efficiently simulatable. Right? But for this talk, the goal is to design these guys, such that has very nice properties that we want. Okay? So one of the properties we want is quantum detail balance. So people already mentioned this. But let's look at the classical case. So classical case, detail balance is this symmetry condition. It depends on the stationary distribution. But for Gibbs state, it's like the symmetry between energy increasing and energy decreasing transitions. These two have to be related by the Boltzmann factor. And classically, you can do that by rejection sampling. Quantumly, this looks kind of crazy. Because quantumly, this L is a superoperator, so it acts on Bras and Katz. So there's kind of four, like, there's two indices there. Now here's four indices. And then quantum detail balance becomes kind of more intricate. But then you can, again, write down, so if these are Bras and Katz with energy, these are energy eigenstates. And you want also some constraints between these two transitions. But this is quite complicated right now. This is formally what it is. Formally, it does tell you the Gibbs state will be stationary. But it's just pretty complicated. It's kind of hard to, this is why designing this is not so trivial, because this just looks very messy.
So what about the coherent drift term? Like, does that have to be the Hamiltonian, or?
Yeah, you can add like a Hamiltonian part, and then you can still get the Gibbs state as a fixed point. But that doesn't quite have a classical analog.
But if the coherent part is not a Hamiltonian, then you won't get the, or at least it needs to commute with the Hamiltonian. Is that right?
It doesn't actually. It doesn't have to. It doesn't have to. So actually, you will see that in our construction, it's important to have a coherent drift term, so that it's. Yeah, and it's not commuting with Hamiltonian. So the coherent part could play a role, but now just to make an analogy with classical, this is what it looks like.
But the coherent part doesn't play a role in the detail balance condition.
Oh, it still plays a role. Like if you can put in your coherent term here, and then it still goes in here. Yeah. Yeah. Right. So here's quantum detail balance. If this is the first time you've seen it, it's crazy, but you could just think of it as like a classical analog. If classically you have detail balance, you can take the discriminant. It's kind of Hermitian under similarity transformation. You can think about spectral gaps. If you prove a spectral gap, you get convergence. So you get all of those basically. Okay.
This is an operator equivalent.
Yeah. So it's lots of equations in this line. Right, so these are the things we want, and here's our results. We cook up an exact detail balance quantum Gibbs sampler. So as a user, you will pick a Hamiltonian, inverse temperature beta, and a set of jumps. And then we give a universal construction of a Lindbladian, or a continuous time quantum Markov chain, with the following nice property you want for Monte Carlo. First, it satisfies exact detail balance. Therefore, the Gibbs state is stationary. Second, using the algorithm Andras described, you can simulate it with basically optimal time, optimal cost. We barely use any ancillas, this old total one, so you need to see logarithmically many. It's roughly not that many. And the Hamiltonian simulation time depends linearly on t, which is what you expect. And it also depends on beta. And this is optimal with individually. We didn't prove it optimality for the product, but individually it's optimal.
So Lindbladian is built on top of A's.
Yeah, so it's a Lindbladian that depends on those things. Yeah. As a black box, it's just a general construction that given all of those, you write down Lindbladian depending on those.
Does the last result give some sort of
Again?
Like the last result for the Hamiltonian simulation time. Is that for you an indicator of the mixing time that you will have in your algorithm?
Yeah, so suppose you want to prepare a Gibbs state, you take this t to be the mixing time. Yeah, I mean, if it mixes, then you don't have to keep evolving it.
Can you give us an example for the Lindbladian?
Yeah, yeah. Yeah, so to reiterate, we kind of just replace the whole path by some set of very carefully chosen operator and resettable ancillas. So you kind of just remove the path. And as Andras mentioned, you can also purify the whole thing. Now you have detailed balance. You can use like a quantum walk. In the spirit of quantum walk, you can write down another corresponding super Hamiltonian that's related to this Lindbladian, such that it fixes on the top eigenvector is the purified Gibbs state, which is this guy. So from here to here is like a standard quantum walk scheme.
Anthony, could you comment on in which sense the new work is better than your existing previous result?
Yeah. So, right. So the previous work has approximate detailed balance. So these kind of explode a little bit because of that. But like in this in progress work, we figure out that we can actually do exact detailed balance. So then it becomes substantially simpler, but it builds upon the previous algorithmic results. Yeah.
So here, psi star is literally the complex conjugate.
Yeah.
It's not
Yeah. Of the eigenstates. Yeah, so even nicer, suppose you want to simulate some lattice Hamiltonian. Or Lindbladian has an even nicer property that its jumps or the Lindblad operators are quasi-local. So what it means is that if you pick your jumps to be single-side operator and you feed into the Lindbladian, you only smear it out a little bit. And this radius is order beta. So if you want a constant temperature Gibbs state, this is local. Essentially local. It has like an exponentially falling tail. So therefore, this is a local algorithm for Gibbs state. And if you take beta to be large enough, this is algorithm for ground state. So for gap ground state, you can set beta to be roughly inverse gap, up to some logarithmic system size dependent. And yeah, so here's the algorithm. If it makes quickly, then you get a ground state. In particular, these jumps only depend locally on Hamiltonian. You can define this jump without knowing what happens globally. But remarkably, these local jumps piece together, and they altogether fixes the global Gibbs state. In some sense, like a frustration-free idea.
So to select beta like that, to get to the ground state, you will need assumption of spectrum. The density of state cannot be too concentrated.
Yeah, exactly. Yeah. But for local Hamiltonian, the first excited state is roughly ordered polynomial in the system side. So this suffices to suppress the excitations.
So I have a question. If I give you Hamiltonian, how many jump operators do you need?
Well, physically, you would choose, for example, like one jump per site.
Yeah, but for arbitrary ones, can you do it with you? So for a given Hamiltonian, do you know I can always do it with 5?
I don't know, but I guess it would. But yeah, we haven't tried, so maybe it works. We don't know. Yeah. I mean, but classically, you definitely want to touch everything. Right, but quantumly, if it gets bigger, then maybe it covers the more space, so you don't actually have to jump everywhere. And if you purify it, the algorithm remains local. So nicely, it gives you a local Hamiltonian, or like local super Hamiltonian, that's frustration-free, and all of them fix the ground state, which is the purified Gibbs state. And then if you run these tools people develop for gap ground states, it's called adiabatic quasi-adiabatic continuation, and you just tune the parameter using as beta, you actually get a log depth circuit for the Gibbs states, if the gap is big enough. So this is all explicit. You can, in principle, write this circuit down. So in the end, let me present the construction. So how do we choose these guys? So the key building block here, as Andras has mentioned, is the operator Fourier transform. Let me just write it down again. So the operator Fourier transform is an operator that depends on a scalar omega. It depends on the Hamiltonian in each jumps in this way. You're going to evolve according to the Heisenberg picture and do the Fourier transform.
Sorry, what is FT?
It's some filter function that smooths out the Fourier transform. It could be like a Gaussian, it could be a window. And roughly this guy corresponds to how smooth you want the transform to be. Right, so if you look at this in an energy basis, it roughly selects a band of transition with energy omega. Right, if you go through this calculation, this roughly corresponds to energy change. And then once you do the filtering, it kind of peaks at energy omega. So what happens here is that you're just decomposing your operator A. It could be a poly, but then you look at the energy basis and then start cutting it like in strips. And each of these strips are labeled by the energy change. Okay. So here's an example. Suppose your Hamiltonian is on the Z. The jumps are X. And then if you do the Fourier transform with energy change 2, it will select the upper right. If you do energy change being -2, it selects the lower left. In more complicated examples, this would look completely crazy. But in this example, it's just these two. Okay. And then here's the
so the Fourier transform only concentrates on 2 delta points on the previous example.
Sorry.
It's supposed to be parameterized by all the possible omegas, right?
Yeah.
But in that case,
I just illustrate for the 2 points. It could be defined for any omega.
In fact, it is defined for all omega.
Yeah, exactly. Yeah. Right. So here you do need all omegas. Yeah. Right. So here's what it looks like. Our construction. It looks very similar to the Davies generator. Also looks very similar to the other physical derivation. But this one is actually very carefully chosen. Right? So we choose this gamma of omega very, very carefully. We also choose a coherent term very, very carefully so that the whole thing ends up having exact detail balance. So this still comes as a surprise. So previously, we thought that this can only be done approximately. It has to be approximate detail balance. But then we somehow figure out that if you choose that coherent term very, very carefully, it somehow cancels out all the errors. And ends up giving like an exact detail balance Lindbladian.
But the price is going to have infinite number of
You do have the integral over omega, but implementing this is efficient.
So when you implement it, you lose detail balance.
Yeah, but it's only up to exponential. So you can get a very high precision. So there's the ideal object.
Yeah, sure.
It has detail balance. You can analyze this. But implementation only has a logarithmic cost to implement this. Yeah. So that's what I mean by exact detail balance.
Why did we do the operator Fourier transforms? Can you tell the
Why?
Yeah.
I mean, physically, roughly, it corresponds to the idea of detailed balance, right? You have some jump A has all sorts of transitions, some increase, some decrease. But now you want to say, well, I want to roughly know how you change the energy. Some of them change by 2, some of them change by -2. Then I want to put a weight like accordingly. This is like you can look at like a classical Markov chain. This is very similar. Right? You would just try to look at energy transitions, and omega, you put the associated weight.
How on earth do you prove spectral gap for that monster?
Well, so it's actually possible. So I've talked to some people working in mathematical physics. Like a very concrete examples is you have lattice Hamiltonian and constant beta. So these are still quasi-local, and you can assume that locally they're gapped, and you can ask whether local gap implies global gap. And people have done that in many cases. Yeah. So that I think is actually doable. So the key feature here is that this is like some complicated monster, but you know that it has exact detailed balance, and it's also quasi-local. So that helps a lot.
Can you explain a little bit more why these guys are local or quasi-local?
Right. So the reason why it's local is because, so in the Fourier transform, there's some time window roughly you want to choose. Like if you use this ft to be like Gaussian with some characteristic time window being beta, then this guy, by Lie Robinson bounds is quasi-local. Right. So somehow the point is that if you want to do detailed balance, the energy scale is beta. And that's all you need to resolve. Yeah. And that smears out this operator, and in the space domain, it's a local patch. Oh, what do you mean by compute? Yeah, implementing this, there's an algorithm that does this, quantum algorithm that does this. Classically, this looks very difficult, but quantumly, you can do this. Yeah, because you use Hamiltonian simulation and some Fourier transform. These are the things we know and love.
Sorry, maybe this is a comment. So I mean, now you have a support which is proportional to beta, right? The number of orthogonal operators that you can have in that region is exponentially beta.
Yeah. So if you want to get like general proof, exponential beta could come up. Because these patches keep growing. So if you want to say that I want to guarantee some kind of ergodicity, then I would guess that you might just need to put a lot of terms.
I see, but that's not a problem.
It might be a problem of the proof, but in practice it might just work without choosing too many jumps. Yeah. I have 1 minute left. Nice. Okay. Yeah, so to summarize, today we'll talk about a design of a quantum MCMC algorithm that complements the perspective of open system. We design this algorithm in the form of a Lindbladian with the nice Markov Monte Carlo requirement. You can implement it, and it has the right stationary state. I probably wouldn't talk about all nice outlook. I'll just stop here. Thank you. Yeah.
Thank you.